Now we have a lemma called CQ, which stands for convex quadrilateral. And this lemma is just going to state some properties about a convex quadrilateral, ABCD. So if I were going to draw such a quadrilateral, it might look something like this. Okay, well, as we saw before in the previous video, the diagonals intersect at an interior point on each diagonal. So if you draw them, two diagonals, that intersection is on an interior point of each one of these two segments, each one of the two diagonals. You could see if it were a non-convex quadrilateral like this, then the diagonals would not even intersect. And even if you did, remember, this is our original quadrilateral. I'll call it D, E, F, G. Even if these two diagonals did intersect, like maybe we extend them to lines instead of line segments, they would intersect right here, which is not only on it's not on the interior of both diagonals. It is on the interior of this one, but it is certainly not on the interior of this diagonal right here. And that turns out that's not even on the interior of the quadrilateral. So clearly, convex, non-convex. And also, the second property, the vertex A, see right here, lies on the interior of the angle BCD. So this angle. If you want to, you can picture this coming out as a ray and that as a ray. And A is on the interior of that angle. And I can make the statement, a similar statement 3 more times. The angle B right here is on the interior of angle ADC. C is on the interior of angle BAD, and D is on the interior of ABC. And number 3, the measure of angle BAD, and I'm just choosing this one. I could have chosen any of the 4. BAD is this angle right here. Well, notice that this angle is equal to the sum of this angle plus this angle. And that's what this statement is going to say. The measure of angle BAD is equal to the measure of angle BAC, that's a part of it, plus the measure of angle CAD. And again, there are 3 equivalent statements I could have made. I could have gone with ADC, that angle. The measure of that angle is equal to the measure of ADB plus measure of angle BDC, and so on. Now, when are 2 given quadrilaterals congruent to each other? Well, they're congruent. Remember, the double arrow means if and only if all 8 of the following hold. And before I even start it, maybe I will draw 2 small quadrilaterals. And I attempted to make them look congruent. Close, but not perfect. A, B, C, D. And then I have to do this one. Remember that if they are congruent, they correspond in the same order. A with W, B with X, C with Y, D with Z. So I have to put W here, X, Y, Z. Well, there are 8 properties. First, let's go through the sides. So I need AB to equal WX. That's the distance. AB is equal to WX. Those are numbers, the distance from A to B. I could have said the measure of the line segment AB is equal to the measure of line segment WX, but this is a little shorter. And then I'll go BC. BC has got to be equal to XY. And then the third side, 1, 2, 3, CD has to be equal to YZ. And then the fourth one, 1, 2, 3, 4, 1, 2, 3, 4, AD has to equal WZ. All right, that's the four sides. Now I'm going to look at the four angles. They've got to be, the corresponding ones have to be congruent as well. So angle A, for example, has to be, measure of that has to equal the measure of angle W, or I could just say angle A is congruent to angle W. They have the same measure. And then B, oops, 2 notches there. B and X, angle B congruent to angle X. 2, 3, C and Y, angle C congruent to angle Y. And the fourth angle, 1, 2, 3, 4, 1, 2, 3, 4. D has to be congruent to Z, angle D congruent to angle Z. So all 8 of those properties have to hold among or between the two quadrilaterals in order for them to be congruent. Now, there are some theorems which will make it a little bit easier for us to determine when two quadrilaterals are congruent. And here's the first one. We're not going to prove this one. We will prove one. Yeah, I think in the next video. Okay, notice that what we have up here, before I go to the theorem, we basically have side, angle, side, angle, side, angle, side, angle. 8 different properties. We had a side, AB. We had the side, angle, side, angle, side, angle, side, angle. If those are all congruent, then the two quadrilaterals are congruent. But it turns out that if you just have side, angle, side, angle, side being equivalent to each other, then you don't have to prove the last 3. This is sufficient. That's enough to prove that two quadrilaterals are congruent. So how will we write that? Well, here we go. Let these two quadrilaterals be given, and they're both convex. We're assuming unless otherwise stated, all of our quadrilaterals will be convex. And then we have A, B, C, and D corresponding to E, F, G, H in that order, the normal order. Well, when are these congruent? If AB equals EF, just like we had, well, up here only I changed the letters. AB was congruent to WX. The lengths were the same. So AB has to be equal to EF. Angle B has to be congruent to angle F. So we have a side, then we have an angle, and then we have another side. BC is equal to FG. Then we have to go to an angle, which will be C congruent to angle G. And then lastly, side, angle, side, angle. One more side, which would be CD equals GH. So once again, if I were to draw two quadrilaterals, let's say that they are, I'm trying to prove that they're congruent. If we have that side, this angle, this angle, this side, this angle, and one more side. If we have this congruence, we know that these two quadrilaterals are congruent. Okay, so we're not going to do a proof, although there does seem to be one in the textbook. So, in the textbook, what we would do is prove that if we have side, angle, side, that we can easily imply or show just from that we'll get this angle being congruent to this angle, this side, and this last angle with this last angle. That's all the proof does. So let's take a look at some potential theorems. Do you think it's not mentioned here, but do you think this could work for a quadrilateral? It says prove it or give a counterexample. I didn't give much room, so it's probably just going to be a counterexample. I think that one is not going to work. Okay, so if we had A, let's see, how would that be possible? I don't think so. Suppose, for example, one of them was a square. If it's a square, we have 4 right angles, and we have 4 equal sides. And on the next one, I'm going to pick not a square, I'm going to pick a wide rectangle. All right. Well, maybe my picture isn't too good here, but let's pretend like this length is the same as this length. I made it a little bit too wide. I intended to make it shorter like this. In this case, we have angle, because all of the angles are 90 degrees. We have angle. Let's see, how do I want to start? We need angle, side, angle, angle, angle. Angle, side, angle, angle, angle. So this holds, but these are definitely not congruent to each other. So that would not hold. That is not a theorem. If you just have angle, side, angle, 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 that's not enough to prove that two quadrilaterals are congruent. What about side, 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 side? Seems reasonable, doesn't it? Well, no, it doesn't. Because if you take a square, equal sides, you could tilt it into a parallelogram like this, where the sides all have the same length, but notice none of the angles match. So in this case, there's not going to be a side, 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 side theorem for quadrilaterals. Remember, for triangles, side, side, side works, but not for quadrilaterals. Number 9, this is a term I've already used actually in this video. What is a convex quadrilateral that has 4 right angles? Convex quadrilateral. Well, here's an example of one. It's a rectangle. A rectangle is a convex quadrilateral with 4 right angles.